Hi chemists, welcome back. In Day 2 notes, we will focus on the meaning of half-life. After this video, you should be able to identify the factor that nuclear stability is dependent on, calculate the half-life for a given radioisotope, and calculate how much of a radioisotope remains after a given amount of time. Let's talk a little bit about nuclear stability. This is important because right now there's 118 elements on the periodic table and only 118. And it seems like every year my students ask me, well, when are we going to get 119 or 120? Well, as it turns out, there are close to 2,000 different nuclei known. Approximately 260 of them are stable and do not decay or change with time. The stability or resistance to change really depends on the neutron to proton ratio, and that's why there's only so many elements on the periodic table. Plotting a graph of the number of neutrons versus the number of protons for each element results in a region called the band of stability. For elements with low atomic numbers, below 20, the ratio of protons to neutrons is about 1. For example, if you look at carbon-12, carbon-12 has 6 protons and 6 neutrons. We know that this is a stable isotope of carbon. For elements with higher atomic numbers, stable nuclei have more neutrons than protons. The ratio of neutrons to protons is closer to 1.5 for these heavier elements. For example, lead-206. The number of neutrons in this isotope would be 124, and then the number of protons is 82. Approximately, the ratio is 1.5. The neutron to proton ratio is important because it determines the type of decay that will occur. All nuclei that have an atomic number greater than 83 are radioactive. And again, back to my initial discussion, do you ever wonder why some atomic masses listed on the periodic table have a parentheses around them? Well, it's because their atomic masses are estimated due to radioactive decay. These elements have unstable nuclei, and they will decay, and so we approximate those atomic masses. Let's talk a little bit about half-life. Half-life is a time, and it is the time required for half of the nuclei of the radioisotope sample to decay to products. For example, if you have 20 atoms of radon-222, this is a radioisotope. The half-life is 4 days. How many atoms remain at the end of 2 half-lives? So here's a nice visual that can help explain this. So there's 20 atoms initially to start. It goes through 1 half-life, that's 4 days. There's 10 atoms left because 10 is half of 20. It goes through a second half-life, which is also 4 days. Total of 8 days now, and we'll see that 5 atoms remain. We can represent half-life graphically as well. So for example, look at carbon-14. However, very seldom do we count atoms, of course. Therefore, it's more appropriate to calculate the amount that remains in terms of mass of the substance. So for example, carbon-14 emits beta radiation and decays with a half-life of 5,730 years. Assume you start with a mass of 2.00 times 10 to the minus 12 grams of carbon-14. How long is 3 half-lives? And how many grams of the isotope remain at the end of 3 half-lives? So let's first focus on the fact that we're looking at 3 half-lives, and each half-life has a time of 5,730 years. So what we do is we multiply the 3 half-lives times that amount of years, and we get 17,190 years. Let's move on to part B. Part B says how many grams of the isotope remain at the end of 3 half-lives. So again, I think it's really easy to do this by saying 2 times 10 to the minus 12 grams times a half, right? That's the first half-life, and then times a half again, that's the second, and times a half again, that's the third. And so you get 2.5 times 10 to the minus 13 grams. Alternatively, here's a really nice visual for students who struggle with the math that needs to occur for this problem. So again, to start, we have 2.00 times 10 to the minus 12 grams. After the first half-life, that amount is cut in half. After the second half-life, that amount is cut in half. And after the third half-life, that amount is cut in half. So that is the math that goes on in order to figure out how much remains. Here's another example. Manganese-56 is a beta emitter with a half-life of 2.6 hours. How many half-lives did the sample go through at the end of 10.4 hours? And what is the mass of manganese-56 in a 1 milligram sample of the isotope at the end of 10.4 hours? So we'll first focus on the fact that we know that the sample went through 10.4 hours, and each half-life is 2.6. So we're trying to figure out how many half-lives is that? How many half-lives did it go through? So what we're going to do is do the 10.4 divided by the 2.6, and that tells us that it went through 4 half-lives. In part B, we know that it's a 1 milligram sample, and we know that it went through 10.4 hours. So what we're going to do here is do 1 milligram, again, times 4 1/2, just like you see there. And so that will give you 0.063 milligrams. I hope this video was helpful in understanding how to calculate half-life. Thanks so much for watching, chemists.